Okay, so I think it's recording. So let's get started. So hello everyone, my name is Suraj Jaiswal and welcome to the second tutorial of the course Simulation of a Mechatronic Machine. Today we will be doing crankshaft modeling in Simscape Multibody software. So as you can see, I have given a basic animation of crankshaft. So what does a crankshaft does? So you can also say that it is a slider crank mechanism where the blue body. So let me show you. So this one, there's a crank connecting rod and there's a piston, and the reciprocating movement of the piston causes a rotation of the crankshaft, as you can see. And in slider crank mechanism, the motion can be the other way around. So let's get started. So today we will be covering this list of contents. So basically, first I will show you what are the requirements for modeling a crankshaft and then how we can model it. So by defining the number of bodies, joints, using rigid transform to have a proper orientation of the body coordinate system. Then we'll check for redundant constraints in the system, and then we'll see how we can plot the results for a crankshaft model, and then we'll do kinematic and dynamic analysis. So the dynamic analysis will be done under different conditions, basically with a constant torque input or a varying torque input, or maybe with some joint frictions. So we'll see to that. So let's get started. So a crankshaft is a rotating shaft that converts the reciprocating motion of the piston into a rotational motion of the crankshaft itself. It is mainly used, this kind of mechanism is mainly used in internal combustion engines, as I already showed you in the first slide. But just a note that in today's tutorial, we will be just using one cylinder piston. So you don't have a crankshaft, but if you have had a crankshaft, it would have been in a direction which is coming out of the plane. So in this direction, it should have been. But we are just considering a planar mechanism. So there will be just a crank, connecting rod, and a piston which can reciprocate in the vertical direction. So let's see what are the requirements to model a crankshaft. Okay. So think in this way, like first you need to have a ground and an inertial reference coordinate system, or you can say global reference coordinate system, and you need gravity. So these are the three basic components that you need in almost all of your mechanisms, right? Then if you look at the figure, you can see you need three bodies, which is this red body, green body, and blue body. You can either name them as body 1, body 2, or body 3. But since you are into mechanical engineering, it's always good to use the right nomenclature. So I call it the red body as crank, the green body as connecting rod, and the blue body as the piston. Okay. Then I need four joints. So as you can see, one joint that is connecting ground and the crank, the second joint which is connecting the crank with the connecting rod, and the third joint with the connecting rod and the piston. And the fourth joint will be between the piston and the ground, which is the prismatic or a translational joint. So you can call them joint 1, joint 2, joint 3, joint 4. And remember the joint 2, which is the joint between the crank and the connecting rod, is called crank pin, and the joint between the connecting rod and the piston is called piston pin or rest pin. You can name them as you like. But let's get started. So first I will open my Matlab. I have Matlab 2019A version. So once you have the Matlab, make sure the folder should be wherever you want to save that. the path of that folder should be mentioned here, as I want it in this folder week 2038 tutorial 2. So I'll put it. Then I will do sm new, so Simscape Multibody new, and it will take a while to open a new file of Simscape Multibody. Let's wait for that. Okay, so I have a basic file here which already have some components by default, as I told you. If you want, you can just go and save as your model and save it the name as you like it to be. But let's get started. So we have this world frame. So we basically have the ground and the inertial coordinate system, inertial reference system. Okay, then we need to define gravity. If you follow my first tutorial, you can figure out that if you double click the mechanism configuration, then by default, the gravity is acting in the negative z direction. So if this is x, this vertical plane, in the vertical direction is y, and this is z. So the gravity is acting in the negative z, which is into the plane of our screen. But we want the gravity to act in the negative y direction. So let's change the gravity to be in the negative y direction and press OK. Okay. Once we do that, then we have our initial requirements. Now we just need to define bodies and joints, and then we will be good to go. Let's remove these things. We don't need them at the moment. So let's focus on this part. So I have a body, three bodies are required: crank, connecting rod, and piston. So by using the solid component block, I can, for example, make a crank. So let's say the dimensions are 0.35 meter or 350 millimeter as the length, 0.050 millimeter as the width, and 50 millimeter as the breadth. So make sure this length is along the x. So x, breadth is along the y direction, and the depth is along the z direction. So that's why I have given this in this order. And I press apply and then F5. So you can see the view is updated. Then let's so let's define the inertia properties. So I want the inertia properties to be based on geometry, based on density. I give density to be density of steel approximately, so 7,800 kilogram per meter cube. Then derived values needs to be updated. Once you do that, you can press apply. Then I want this body to be red in color. So I want the graphics visual to be updated. So this color combination code is red, green, and blue, RGB. And I want it to be red. So I increase the value of red. I press enter or apply, and then F5. The color is updated. Then I need to define two frames, one on this. So okay, first R is already there by default, the which is at the center of the body, and I want two frames, one in this and the one at the back over here. Okay, so and I don't want this port R to be visible. So if you see this block, this R is already visible. I won't be using that in the modeling. So let's make disable it so it won't be visible, and let's define new frame. Okay, first we need to update because we have done changes. So F5 and then new frame. Now I want to make the new frame based on geometric feature, then select the surface and then select use selected feature. So this is a centroid of minus x surface. Okay, you press save. So F1 is there already. Now I need to define F2 on this one, which is in the positive x direction. So new, based on geometric feature, select the surface, use selected feature. So you can see it's there, and select. And if you press OK, things will be fine. So let's press OK. So you see by default frame F1 and F2 are already here, and I try to shape it such that I know the crank is something like in this shape. It's not actually necessary, but I always try to shape my blocks in a way how I'm defining the physical system. And let's say it's crank. Okay. Now if I just copy paste this block, or let's say uh, select it, press Control and drag, then I can define my connecting rod. Okay. And remember, the length of the connecting rod is different from the crank. Otherwise, all the other things remains the same. So in the length, it's 1000 millimeter. So I do it 1 meter. I press enter and then F5. So you see the length is updated, and at the same time, the frames F1 and F2 are also adjusted accordingly. And about inertia properties, derived values, everything remains the same, but I just want it to be a different color. So now I want this to be, let's say, green in color. Okay, not this one, sorry. So I make the green value to be more than the other. Press enter, then press F5. You see the body is green now, and and the frames are already there, F1, F2. So we don't need to do anything else. And we press OK. So we have our connecting rod as well, correct? So let's increase its length a little so that I know it's slightly larger than the crank. Okay, now we need a third body, which is a piston, and you again model the third body using the solid component block. So this solid component block, and let's rename it piston. Okay, if you double click this, I want the shape to be cylindrical. So I choose the cylinder shape, and it's asking me what should be the radius and the length. Let's say the radius of the cylinder is, let me check the slides, it's 100 millimeter, so 0.10 meter, and the breadth is 150 millimeter, so 0.15 meter. And I press apply and F5. So you see the, okay, let's see the reference system as well. So you see the shape is updated. Then I define the inertia properties to be same based on geometry, based on density, and the density to be the density of steel as in my previous bodies, and update derived values. Now I want the color of the block to be, let's say, blue. So I'll update the graphics, the visual properties, and I increase the value of blue. So then I press F5. So the color is updated, correct? Now I want to define one extra. So by default, this frame is R is at the centroid of the body. Now I want to define one extra frame which is at the bottom of this body, the bottom surface. So let's go to new frame based on geometric feature, then select this and use selected feature. So the center of bottom surface is there, and we press save. So now you see we have our piston body ready as well. So what we do, we just press OK, and let's shape this. It's not really required, but it's always good. And let's orient this so that you remember F1 is at the bottom and R is on the top. So Control R to rotate this. Yeah, something like this. Correct. So we have the bodies available already. Let's go back to the slide and see if we have covered most of the things. Okay, so we already made crank connecting rod. We already made this cylindrical block as well, which is the piston. Now we need to model the joints. So let's go back to this slide, to the software. So if you see, if you think in, we need three joints, four joint in total, out of one, which one has to be a translational or a prismatic joint, and the remaining three, the first thing that comes to our mind when we think of such a system is we can say, okay, since it's a planar mechanism, so let all the three joints can be revolute joint, so that we know the rotation is about the z-axis, which is perpendicular to the plane. So that's fine. So my first instinct says let's make all the joints using revolute joint block. So I just searched the revolute joint block, and I'll name it as, for example, joint 1. Okay. Remember, I want to connect the base frame to the ground reference system, since the first joint is at the bottom and it's connected to the global coordinate system or inertial reference system. So the base is oriented such a way, and the follower will be connected to the crank. Okay. Mm, okay, perfect. So now we want this joint in such a way that uh, initially the crank makes an angle 45-degree with the global coordinate system in the anti-clockwise direction. So if this is my coordinate system x, y, and z, then I want this to be 45-degree in the counterclockwise direction, which is taken as positive. So I need to define some initial state target, which is position level. So I specify the position level state target, and I say it's, since I'm using degree, I say it's 45-degree, and I want the priority to be high, and then I just press OK. Fine. I have my joint 1 ready, and it's a revolute joint. If you want, you can copy this for joint 2, but remember we gave some initial position condition for joint 1, but we don't need it for joint 2. So if you're copying this block, remember to remove that initial position condition, or else you can just type revolute joint block again. Since it's joint 2, first let's rename it, and it's crank pin as per the name, and you don't need to define anything. Things can be the default values, but let's orient this using control R. So the base frame of joint 2 will be connected with the crank, so it can be here. Okay, I don't need to do the connection yet, as you can just place it, and the block joint 1 can be here. Then I need another joint which should connect connecting rod with the piston, correct? So let's copy this one, control and drag. Let's say it's joint 3, and I name it as piston pin. Let's say it's piston pin, and it it does not need to have any initial position condition, and it can be by default. And the base will be connected to, for example, the connecting rod. Let's decrease the size so that everything can be in one screen. So the base will be connected to the connecting rod and the follower to the piston block. But now comes the tricky part. Remember, by default, revolute joints revolve around z-axis, correct? So if this is my surface, for example, if this is x, my left hand, this is my left hand. So if this is x, this is y, then z is pointing out of the plane, correct? So the revolute joint is rotating about this z-axis. But if you see this block, piston block here, if you go to the frame, for example, or let's not go to the frame. Okay, let's go to the frame. If you go to this frame, you see this frame is defined such a way that the longitudinal direction of this body is in the z direction. So if you simply connect this revolute joint with this piston, what will happen is, suppose you have a cylindrical body like that, and it will rotate it like this, but we don't want this body to rotate like this. We want this to go up and down, and the revolute joint is connected somewhere here, correct? So we don't want this rotation, we want this to go up and down, so can this joint can rotate like this, so about z-axis. So there are two ways of changing the orientation. One is by using this frame axis, so you can actually orient this frame F1 according to as you like. But let's do the alternative way, which is by using rigid transform, so that you can actually know how to use the rigid transform. So let's say it's called rigid transform 1. Okay, correct. So this rigid transform, the base will be connected to, let's say, controller, so the base will be connected to, let me place it such that I can have space for everything, or maybe have zoomed it too much. But anyways, so this rigid transform needs to be connected between joint 3 and the piston, because I want a uh, change in the orientation of the axis. Okay, I will do it in such a way that the base is connected to the joint and the follower is connected to the piston. So let's double click this and open this. There are different methods of doing this, but I will do it using aligned axis method. So what happens in aligned axis method is I can define the pairs. So the first pair, which is saying that base is connected, so the z-axis of the base, so let's say the base is connected to the revolute joint, right? And I want the z-axis uh, of the revolute joint, so the z-axis of the revolute joint to be oriented, for example, in the x-axis of the follower frame. So a revolution about z-axis of the base will cause a revolution in the x-axis of the follower, and the follower is connected to piston. So if this is the piston and this is z coming out of the plane, for example, towards me like this, then, and this is x. So I want this rotation to be about x, so that like this can go up and this can rotate like this. Okay, so let's say that, and let's say the x-axis of the base frame is projected onto the y-axis of the follower frame. Okay, So this is how we are doing the alignment of the axis, correct? And when then we press OK. Okay, now this block is ready to be connected, but we'll not do the connection yet. Okay, now the piston block is connected to the ground using a prismatic joint or a translational joint. So let's search for a prismatic joint, and the prismatic joint is connected such that you can like orient this, or you can keep it as it is, as you like. And let's say it's joint 4, which is a prismatic joint. Okay, so in prismatic joint you don't need to do anything, so it can be at the moment as default, and you will be connecting this prismatic joint with the piston. But remember, the piston the piston in its local coordinate system is moving in its z direction. So for the piston, the z direction is like this, but we want that uh, z direction to be in the global y direction. Then then only we can see the piston to move in the vertical plane or in the vertical direction, right? So we need another rigid transform. So we can simply copy this. Okay, let's remove uh, these blocks here. We don't need them yet. So the by default the blocks that come. Okay. So we need another rigid transform such a way, let's orient this using Control R, such a way that the base will be connected to the ground. The base will be connected to the ground, and the follower will be connected to the prismatic joint, which is joint 4. And I will use the same axis aligned axis method, and I will define the pairs now as follow. So follower frame will be connected to joint 4 and base to the world frame. So a movement in the z axis of the follower frame will we need to project it to the y axis of the base frame. So z axis in the translation of the piston in its local z direction will be projected onto the y direction of the world reference frame. And the other pair needs to be defined accordingly as you define this rigid transform 1. So the uh, movement in the y direction of the follower frame will be in the x direction of the base frame. So similarly how we define this one. And then we press OK. Fine. If you have done so far, then we have basically made our basic components needed to model the system, and it's in place now. So let's go ahead and join the system. By the way, let's see in the presentation if we are following as per the presentation. So yes, we have covered this slide. Then I have already showed you how to model the things. Okay. And now we just want to, okay, by mistake, I think I pressed. Okay, so let's go back to our model. Okay, so now we just need to connect the systems. So the base frame of the joint 1 is connected to the world reference frame. Follower frame will be connected to F1 of the crank. Frame F1 of the crank. Then F2 of crank to the base frame of joint 2. Follower frame of joint 2 to the frame F1 of the connecting rod. F2 of the connecting rod to the base frame of the piston. Follower frame of the of the joint 3, follower frame of the joint 3 to the base frame of rigid transform, then follower frame of rigid transform to frame F1 of the piston, then frame R, which is the body reference frame or which is at the center, needs to be connected to the follower of the joint 4, and accordingly base of joint 4 to follower of rigid transform and base of rigid transform to the world reference system. Okay. Now, if you have a very complicated system and you are unable to, I mean, of course, you can connect the system as you like, but for some reason, if this connection becomes complicated, you can define the world frame again, and it will mean the same thing. And you can connect this block to this block. It will mean the same thing. But since it's a relatively simple structure, so we will not do that at the moment. So this is how our model looks at the moment. So now I want to have a cross check whether it's correct or no. So let's run the simulation model and let's see the visualization. So by default, it will compile and then the mechanics explorer window comes. By default, there is something happening, but we can't see it. It's because we need to change the view. So the Y will be up and X5 front, and then we need to press this front view. So once we do that, we see we have our system as we wanted it to be, and let's see the animation. So I think it's animating it how we wanted it to be, correct? Yes, that's what we expected. It's that the piston will reciprocate in the vertical direction and the crank will make a revolution. But since we are observing the system under gravity, and for that reason, the crank is kind of oscillating like a pendulum under the effect of gravity. And also, if you see the initial condition, so this one makes an angle of 45 degree with the inertial reference frame. So X, Y is Z. X, Y, and Z coming out of the plane. Uh, I always like to use this visibility of frame so that I actually know what's happening. You can also make visibility of center of mass, but I don't do that. So when you run it, you actually see so which frame is going where and how the rotation is happening. So we have our system kind of a preliminary model ready. But remember, we had no idea about what joint to use and what not. We kind of made an initial guess, correct? So let's go to our model again and let's see if our initial guess is actually right or wrong. So if we go to the analysis part, then Simscape, then statics viewer, you see, first of all, it's a 1 degree of freedom system. Why it is a 1 degree of freedom system is a rotation of the crank will cause uh, the vertical motion of the piston, or the vertical motion of the piston will cause the rotation of the crank. So either way, there is only 1 degree of freedom. By defining any one of the following motion, you can have a motion of the entire system. So the degree of freedom will be 1, which is there. Very good. And of course, the number of bodies we have defined 3, number of joints and everything, it's there. And remember, the number of constraints, it's not coming here because this number of constraints, it's like if we are putting some additional constraints using the constraints block, then it will appear. But since we are using in the joint, and if you see the number of position constraint equations, in total there are 5. And the number of position constraint equations non-redundant is 2. So this clearly indicates that there are 3 additional position constraint equations which are redundant. Now the problem is we don't want redundant constraints in the system. For simple case, Simscape is able to handle the redundant constraints, but maybe for complicated case it may not be able to handle such redundancy. So in that situation, it's always advisable to get rid of the redundant constraints. And how you can do that? For this system, it's maybe quite simple. Uh, you can play around with the joints. So if, for example, if you have a prismatic joint, let's keep it as it is. But the other joints, the other three revolute joints, you can play with those joints. You can change the joint type and see what's happening. Okay. In this tutorial, I will play around with this joint 2, which is a crank pin. So I defined it using revolute joint, correct? And revolute joint incorporates something like in 2D, it gives you two additional constraints. I mean, it incorporates two constraint equations. So let's use instead of this revolute joint, I will use bearing joint, for example. Okay, and the bearing joint also has base and the frame. Let's orient it using Control R, and I want to replace this joint with this bearing joint. So let's remove the connection first, remove this part, include the bearing joint, rename it as joint 2 crank pin and bearing joint, right? Now, once you have done that, bearing joint can be as it is by default values. But if you just double click and see how is it, so the bearing joint can have three primitive joints in three rotational axes. So three rotational primitive joints can be there, and one translational primitive joint can be there, which is in the z direction. So this is how you can define a bearing joint. But at the moment we keep it as it is and we just connect it with the system. Now, since we have done this already, you may go ahead and run the simulation model and see what happens. So if we see the visualization window, you see this is not what we desired. I mean, the piston is now oscillating in the negative y direction, and that's not we want, correct? We want it in the vertical direction. Why this is happening? Because we have not defined enough conditions, we have not given enough conditions to our system. So let's go and give some kind of position condition to the prismatic joint. So if you double click this, if you go to the state target position level, now see, I don't know what should be the exact value. Like initially, if the crank is at 45 degree, then what should be the exact distance? I mean, of course, with a pen and a paper, you can calculate that. But let's say I'm giving a random value, which is 1.3 meter. And I say its priority to be low because I really don't know if that's the exact value, and I press OK. Perfect. And then I run the simulation again. And now if you go and see this visualization, things are fine, right? That's how we wanted our system to be. And if you see the initial condition, which is at time t equals to 0, it is 45, and this is at a distance which is approximately 1.3, or maybe it has defined already. We'll see to that. So let's go and see, have we achieved what we wanted by changing the joint? So if you go to analysis, Simscape, statics viewer, let's minimize this part. So now see the degree of freedom is 1, which is already there. Number of position constraints are now 2, and the non-redundant ones are also 2. So there are no redundant constraints in the system. and we got rid of the redundant constraints by changing the joint type, which is what we wanted. So we are on the right track. And now let's go to analysis again, Simscape and variable viewer. I just want to show you like the variables or the initial conditions, position or velocity condition that we give, how it behaves. So you remember for joint one, we gave a position condition which is 45 degree and priority is high, and the solver is able to meet that condition. Whereas this position condition that we gave to the prismatic joint, the solver is kind of approximately it's close to that value. It's because we set the priority to be low and we gave a target value which is 1.3. But if you see in reality, the exact value at time t equals to 0 should be 1.291378, something like that. So the solver by default, not the solver, but from the from the initial configuration, the system by default calculated its value to be this, and this is at this point the simulation starts. So you can see whatever changes you do, and whenever you do any changes, make sure you check all these analysis part, the statics viewer and the variable viewer. Okay, so we have a system which is up and running. Let's go back to the slides. So we have a system which is up and running, and we have removed the constraint redundant constraints, and fine. So now let's see how we can see the results for such a system. So for example, I am interested in obtaining the position and velocity of the prismatic joint, okay, or the location of the piston. So if I double click this, I need to activate the sensors of this joint. So let's activate the position and the velocity sensor. So the moment I do that, there will be two additional marks symbols here, which is position and velocity. I press OK. So you see the position and velocity, it comes now. Okay. Okay. So this is the signal that is coming from the physical system. I need to convert it in the Simulink signal. So for that, I will use this block, which is physical system Simulink converter. So converting the physical system signal into Simulink signal, and this is scope with the help of which you can actually see the results. So I use this block. Let's rename this one as, for example, position, piston position, or let's keep it position only. Okay, and this can be in short PSS converter. So short form, and then this scope is for position. Similarly, we can just copy and drag this to say we want to see the velocity. Okay, and velocity, correct. So what we need to do is just we need to connect the position sensor signal to this block and velocity sensor signal to this converter block. And now we need to run the system again. So we need to run the system again. Now if we run the system again, and if we double click this, you can see the value of the position of the piston or the joint, prismatic joint, and the velocity of the piston or the prismatic joint. And it is how it should be with the way we have defined our system. Okay. But now if you want to log these signals, you can just right click this signal which is sending from the converter to the scope. You can select it and then right click log selected signal. Okay, this mark will appear. And now if you run the simulation again, this data inspector will be highlighted. So if you go to the data inspector, you can, it's opening. Okay, so you can plot the position, you can plot the velocity as you like. Okay, so let's go back to our model. Okay, so we already have a system up and running. We know how to plot the data, save the data, remove redundancy if there are any, and everything is as we expected it to be. But now let's go ahead and do a kinematic analysis and a dynamic analysis for the system. So what do you mean by kinematic analysis? Kinematic analysis is something like we have a system, for example, 1 degree of freedom system, and we want to define the motion of that system using some function. So let's say we want to define the motion of this joint, or let's say the motion of the crank basically. So if we go to this uh, joint, we want to provide it some actuation, okay? And we want to define the motion. I mean, kinematic means no forces involved. So things are, instead of defining a torque, we want to define motion. So the motion, we want to select it provided by input, and the torque can be computed automatically, right? Once you do that, press OK, and by default you will see there will be additional mark here which is Q. So basically send, it needs some input for the position. We want the crank to rotate at a constant angular velocity of, let's say, 5 radian per second. And remember this, everything in the mechanism, since it's SI unit, so everything, it demands, the position it demands, the unit is in radian. So we need to define a motion input which is in radian per second. So the angular velocity should be in radian per second, right? So let's use a ramp function. So if you double click ramp, since we need to provide a constant angular velocity, so we can just double click this ramp. So the slope of this, so it's like defining velocity versus position plot, and its slope should be 5. So this 5 means 5 radian per second is the angular velocity of the input function that we are giving. Correct? Start time will be 0. Initial output. You remember the crank is initially at 45-degree angle. So I want this to start from 45-degree angle, which is anti-clockwise. So positive, you don't have to give anything for positive. You need to define 45, which will be pi by 4. Since it's radian, so pi is in radian. So pi by 4 radian, correct? And you press OK. So my input function is there. But now this is the function that is coming from the Simulink model, correct? And I want to convert this signal into physical system signal. So I need to use this block, which is Simulink PS converter. So I will place this block here and I will connect this with this with this, and the ramp function with this. Okay. Now, if you go ahead and run the system, it will show you an error. Why? Is because we have not tuned this converter. What I mean by that, if you double click this, so you know that in multi-body system dynamics, we have constraint equations and then we need a Jacobian for that. Okay, over here the input constraint is already there, but we have not defined what will be the Jacobian of that constraint. So if you go to this input handling, filtering and derivatives, instead of zero derivatives we want filter input and its derivatives calculated. Okay, filtering order can be second order because we need the second order refers to velocity and acceleration. Okay, and this input uh, filtering time can be by default 1 millisecond. So press OK. Perfect. So now if you go ahead and run your model, now it's already there. Let's see the animation first. So before seeing the animation, what am I expecting? I'm expecting that there's a crankshaft mechanism which have provided an input of 5 radian per second anti-clockwise, and it's a constant angular velocity. So I want the crank to rotate clock anti-clockwise uh, at a constant angular velocity at for 5 radian per second, and the piston to have a reciprocating motion which can be sinusoidal approximately. So let's go ahead and see. So if I play, so yes, the crank is rotating anti-clockwise and the piston is reciprocating as it should be. So visualization wise, we are on the track. So that's a good news. So let's go ahead and see the plot. If we go and see the velocity plot, you see there is constant velocity of the piston, and it's obviously reciprocating. And if we see the position, it's almost sinusoidal, correct? So that's what we wanted from this kinematic analysis, right? So we have, okay, let's go back to the slides again. So we have covered this one. Then I already showed you how to do the kinematic analysis, and I have also shown you how the system will behave and how will be the animation. Okay, but now one important point is in a kinematic analysis system, uh, what do you think? What will be the degree of freedom? So in my mind, I know by default when there was no input signal, by default the degree of freedom was 1, correct? But now I gave an additional input constraint, which is basically a constraint that is driving the system. So for a kinematic analysis system, the degree of freedom will always be 0 because that additional constraint uh, compensate that degree of freedom that was present. So whenever there that function provides some input, then only the mechanism will move, otherwise not. So that means the degree of freedom is 0. But if you go to this analysis, Simscape, statics viewer, it did not show the number of mechanism degree of freedom to be 1, to be 0. I don't know why. It should have, but maybe we are defining it as a separate block. So maybe it's for that reason not showing that. But always remember that for a kinematic system, the degree of freedom for kinematic analysis, the degree of freedom will be always 0. Okay, that's why it's called a kinematically driven system. So now let's go ahead and let's carry out the dynamic analysis. So what happens in dynamic analysis is instead of this input, we say the input to be a torque. So let's say a constant torque, for example. So let's have a constant block. Then I'll just remove this one. Have constant block. And let's say we are providing a constant torque of say minus 20 Newton meter. So why minus? Minus means clockwise. Okay, and 20 Newton meter. So Newton meter is SI, and I press OK. Now remember, when we were doing out the kinematic analysis, we were actually giving position as the input, but now we want torque to be as the input. And by the way, before proceeding, if you want to save the kinematic analysis model separately, you can just go ahead and save it and then copy all the components in a new file again and carry out the dynamic analysis. But for simplicity, I am showing all of them in one file, but you can save new files as you like, because it's always easy to have separate files for the kinematic and dynamic analysis, correct? So yes, if you come back to this joint, it was taking a position as the input, but now we want uh, or the motion as the input, but now we want torque to be the input. So we need to double click this. We need to go to actuation system instead of, and the torque, instead of automatically computed, we are provided by input, and the motion needs to be automatically computed, and we press OK. Correct. Once we do that, uh, what we need to do is simply connect this block with the converter, and now we will run the system again. So if we run the system again, what am I expecting before seeing the animation? I'm expecting that minus 20 Newton torque, so it should rotate clockwise with a constant torque. The crank should rotate clockwise with a constant torque, which is 20 Newton meter. So if it does that, what will happen? A constant external torque is being provided, so the system will end up kind of having a very high speed. So let's see. So if we run the system again, so it's rotating clockwise, which is good. And if you see, the velocity of the piston or the entire system is kind of rampifying, so it's kind of increasing. See it again. Yes. So this is what we expected, correct? Now, if you want to see the same thing in the plot, let's go back to this. You can double click the position. So basically the position of the piston is first, the frequency of that oscillation is kind of normal, but then as the speed increases, the frequency becomes very high. That's what we were expecting. And the velocity of the piston will just increase, like, I mean, it will oscillate, but with a higher frequency and a higher uh, amplitude. That's what we were expecting. Now, if you want to compare this result with the previous kinematic analysis result, go to the data inspector. Okay, so the run 3 is the present one. I want to compare the velocity. So the velocity is kind of amplifying. And the previous run was the kinematic analysis, and I want to plot the velocity again. So you see in the previous run, the velocity was constant because it was kinematically uh, actuated. Now it's amplifying because of the constant torque. So that's good. We can see we have carried out the dynamic analysis successfully, correct? But now let's say if you don't want to have the constant torque, but you want to have a varied torque. For example, let's say you want a variable torque or the torque that is changing with time. But before that, let's go back to the slide so that we are as per the slide. So we have already covered this part, which is providing with constant torque input with the dynamic analysis, and I already showed you how the system will behave and which is as per the logic. So that's really good. We are on the right track. Next, we need to do out. Okay, let's go back to this. So next, we need to do out dynamic analysis with varying torque input. So instead of this constant block, let's remove this. Let's remove this. And we need a torque input which is changing with time. So let's say we are using signal builder block, correct? So signal builder block, if you double click this, you can provide your signal accordingly. So let's say my initial torque at time t equals to 0 be minus 20. Okay, and enter. And then I need to change this torque to 0 between 4.5 to 5 second. So at 4.5 also, uh, okay, first, okay, let's say at 4 seconds it's minus 20. Then first I need to define this change to be at 5 second it should be 0. So at 5 second it should be 0. And now I can actually define this point to be 4.5. Otherwise it will cause problem because you cannot define graphs like first 4.5 and then 4 like that. So at 4.5 it's minus 20, but at 5 it's 0, and I want to be 0 throughout. So even at time 6 I want it to be 0, and enter. So this is how my signal will look, correct? And I want this signal, this input torque. So remember, the t is the time which is in second for 10 second, and y is the input torque that we are giving, which is in SI unit, Newton meter. So minus 20 we defined only, and then you can close this block. Uh, Before proceeding, you remember, if you have not done that already, you can just make sure the input to this joint should be the torque input and not the position input or the motion input. So since in the last time it was already done, so we don't need to do that. But in the slides, it's mentioned this step again. So just for someone, if they have skipped the constant uh, torque input part. Now you just need to connect this with the converter and run the simulation again. So if now we run the simulation, what am I expecting? I am expecting uh, that the crank will rotate, since it's minus 20 between 0 to 4.5. So the crank will rotate in the clockwise direction with a constant torque of 20 Newton meter. And since it's constant torque, so the velocity will build up, velocity of the piston will build up, but then the torque becomes 0. So I'm expecting the velocity to be constant after that, obviously reciprocating. So let's see the animation. So if I press play, so I can see it's building up, but now the building up is not there after 4.5 seconds, and it's okay. So if you have not, I mean, it's not always easy to visualize this, and of course it's out of experience you can say, but visualization is just for your understanding. It's not very scientific. Scientific is the plots. So if we see the velocity plot first of all, so you see that's what we expected it to be. Between 0 to 4.5, the velocity is uh, amplifying or increasing, and then after that the torque is 0, so the velocity is constant. So that's what we expected, right? Correct. And if we see the position plot, so it's reciprocating with some frequency, and that frequency is increasing, but then the torque becomes 0 and the frequency remains constant. Okay. If you want to see this plot with respect to the previous run where we used constant torque input, we go to data inspector again, and now, okay, let's change this value to the pink for examples. Okay, so in this run, this is the velocity plot is, so it's increasing and then remaining constant. Obviously, it's reciprocating. Also the frequency is changing. Whereas this plot is for the kinematic analysis, okay, where the frequency of oscillation is constant and the velocity is also reciprocating, but it's constant, not increasing. Whereas for constant uh, torque, you remember this for this blue one, which was increasing throughout. So you can actually compare your systems and how it is behaving. So this this pink one is the one, yeah, this one that I selected. This one is the one. Let's change the color. This red one is the one we have it now. So you can compare the signals. Let's go ahead and now, okay, first go back to the slide so that we don't mix up. So I have already carried out the dynamic analysis using varying torque input, and I already showed you how the system will behave for such a input. And now let's proceed. uh, if we want to add friction uh, to the model, let's say joint friction. So let's go back to our model. So we want to define joint friction because in reality the friction is present in most of the systems. So if you want to add friction, you can do it in two ways, the joint friction. And let's say suppose we are using the joint friction to this joint 2, which is a bearing joint. You can give it to anyone, but be careful, especially with joint 1, since you are providing the initial torque or the motion input to it. So let's say we are giving it to joint 2 and we want to define it in such a way. Uh, okay, there are two ways of defining it, as I have told you. If you have this, okay, let me go back here. If you have this add-on already added to your Matlab, which is Matlab multiphysics library, multibody multiphysics library. If I press multibody here, so this one, Simscape Multibody Physics, Multiphysics library, I have already installed it, but when I go to my system, and this is the this block is kind of readily available implementation of friction. You can use that. So if you go to rotational hard stop friction, if you are able to do that, well and good. Otherwise, when I press it, it causes me error because I am working on the server. So I save all my files on a server, and this add-on is not allowing me to install that uh, the add-on to in the server because of the path that I'm using for the MATLAB and for security reasons, of course. So I'll go with the other way around, which is also simple. So I'll define crude friction. So what I need to do, if you double click this bearing joint, if you go, since in the bearing joint the rotation is about the z-axis, so if you go to the revolute primitive, go to the internal mechanics. So the internal mechanics damping coefficient. So what does friction does? Friction basically restricts the motion between two bodies in contact. So if we provide damping to the system, it will serve the purpose, right? So let's say I'm providing the damping to be 0.01 Newton meter per degree per second, whatever the unit will be. And let's press OK. So I already have the friction in the crank pin or the joint 2. And now we'll run the simulation again. So we have defined a crude friction at joint 2. Okay. So what am I expecting? I'm expecting that obviously with the varying torque input. Okay. This is the varying signal bit. With the varying torque input between 0 to 4.5 second, the the velocity will increase but then we already have friction, so not with that amplitude, but maybe with the smaller amplitude, and then the torque becomes zero, but the friction is present, so it will dampen the motion, so the velocity will decrease. So that's what uh, I can think of. So that's the most simple, the simplest way of analyzing a system. I'm just giving you an example. So you should also brainstorm and see. I mean, how obviously you are modeling stuffs, but then think logically. If your model is not according to your logic, then there is something wrong either with your logic or with the modeling. So both of them should be on the same side. So let's see. Let's run this. So yes, I can see the motion. Okay, that's interesting. So what happened? Run it again. So what happened? So between 0 to 4.5 second, it is kind of increasing the velocity, but then the velocity decreases. Mm, as per our logic, that's how it should be, right? But we actually don't know, like, is the velocity greater than the previous one or not? So before that, let's see how is the velocity. So the velocity increases, then it decreases, which is logical, correct? How is the position? So the position, the oscillation frequency first increases, then decreases. Yeah, that's how it should be. But now we don't know whether the magnitude with which it was oscillating, it's greater than, equal to, or less than the previous run. So in the run where there is no friction. So let's go to this one again. And okay, run 4 was the one where we had no friction but varying torque. So let's plot. Okay, everything is mixing up with the color. Try to use different color, guys. Okay, so let me remove some of them. So this one, the purple one, was the kinematic analysis. Okay, okay, let's explain everything here. So this purple one was the kinematic analysis. Okay, then this blue one was the one with the constant torque input. Then this one with the varying torque input. Okay, and then this red one is the one that we defined now, varying torque input but with friction. So compared with this green one, you see also the velocity is increasing uh, till 4.5 or till 5, but then the amplitude is less than before because of friction. And then the previous one, there was no friction and zero torque, so the velocity remains constant. Whereas in this one, there is no torque, zero torque, but friction is there. So the velocity decreases and the frequency increases. Sorry, the frequency also decreases. So that's how you can analyze different system. Obviously, you can save the system and save the data, like save, import, export, whatever you like. But that's how you can do the kinematic and dynamic analysis. Let's go back to our slide. Okay, where is my slide? This one. Okay. So we have already covered this part, and then I already showed you how will the system behave and how you can compare it with the previous run or with the previous system where there is no friction. So for today's tutorial, that's all. If you have any questions, do contact me on my email address, which is suraj.jaiswal@lut.fi. And if you like this tutorial, then thank you so much. And I hope this is helpful for you. And that's all from me for now. But thank you.